Welcome to this video on using the Radial Basis Function, or in short, RBF kernel, to improve classification accuracy in support vector machines. Sometimes data isn't nicely separated by a straight line, and that's where the RBF kernel comes in. We'll start by importing the necessary libraries. We need NumPy for numerical operations, Matplotlib for visualization, and several modules from Scikit-learn, including the SVM implementation, data generation tools, and evaluation metrics. To demonstrate the power of nonlinear SVMs, we're generating a non-linearly separable dataset using Scikit-learn's make_moons function. This creates two interleaving half-moon shapes that can't be properly separated with a straight line. We're adding some noise to make the problem more realistic. Here, we can see our dataset visualized. Notice how the two classes form curved moon-shaped patterns. If we tried to separate these points with a straight line, we'd always misclassify some of the data. This is exactly the type of problem where nonlinear SVMs shine. Now let's implement our SVM classifier with the RBF kernel. We're using Scikit-learn's pipeline functionality to first standardize our data, which is an important pre-processing step for SVMs. Then we are creating an SVC classifier with the RBF kernel. The gamma parameter is set to scale, which is a good default that adjusts based on our data's variance. To understand what's happening under the hood, we need to visualize the decision boundary created by our RBF kernel. We've defined a function that creates a fine mesh grid over our feature space and predicts the class for each point in this grid. This allows us to see exactly how our SVM is separating the data. This visualization reveals the power of the RBF kernel. Look at how the decision boundary curves to perfectly separate the two moon shapes. This nonlinear boundary would be impossible to achieve with a linear kernel, which can only create straight-line decision boundaries. For a proper evaluation, we are splitting our data into training and testing sets. We'll use 80% for training and 20% for testing, which will give us an unbiased assessment of our model's performance. The results demonstrate the effectiveness of the RBF kernel. We're achieving 96% accuracy on our test set, which confirms that our model is successfully capturing the nonlinear patterns in the data. This classification report provides additional metrics like precision, recall, and F1 score, all of which are perfect for both classes. For comparison, let's see how a linear kernel performs on the same data. We're creating another SVM classifier, but this time specifying a linear kernel. Everything else remains exactly the same, including the standardization processing. This side-by-side comparison clearly illustrates why nonlinear SVMs are so powerful for complex datasets. On the left, we see the RBF kernel creating a curved decision boundary that nicely separates our two classes. On the right, we see the linear kernel struggling with a straight line boundary that misclassifies many points. Notice how the linear kernel's accuracy is significantly lower than the RBF kernel's. This demonstrates how nonlinear kernels can dramatically improve classification accuracy when dealing with data that isn't linearly separable. All right, in this demonstration, we've seen how the RBF kernel transforms SVMs into powerful nonlinear classifiers. Thank you for following along.